Have you ever wondered how things float? Why a huge ship floats, while a tiny stone sinks? It all comes down to buoyancy.
We know that objects fall towards the earth because gravity acts on them. But if gravity acts on everything, why doesn't everything sink? Imagine a submarine that is stationary underwater. We know gravity is acting on it, but the sub isn't sinking, so there must be a force opposing gravity. We call this force buoyancy. In this video, we will examine buoyancy and why some things float while others don't.
First, let's review density before we move on to buoyancy. Different materials have different densities. It's a measure of how much mass there is in a given volume, and is determined by the following formula. Density equals mass divided by volume.
Density is an intrinsic property, which means it depends on the material but not the shape or size of the object. So while a gold bar may weigh more than a gold coin, they have the same density. And while a kilogram of rocks and a kilogram of feathers have the same weight, they have very different volumes and therefore very different densities.
Here are typical densities for different materials. Do you see how density and buoyancy are related? Generally, rocks and metals are more dense than water and sink, while styrofoam and wood are less dense than water and float. So, we see that density affects buoyancy.
But it can't possibly be everything.
Many modern ships are made of tons of metal that are more dense than water, but the ships still float. The boats are floating because they are not just a solid block of metal. Their hull is made of metal, but the inside is full of air and room for people and cargo. The ship with all the space inside displaces a greater volume of water than if it were squished into a block, in which case it would actually sink.
Therefore, we now know that both the density of the material and the volume of the object play a role in defining buoyancy. With this in mind, let's take a closer look at how things actually float.
Here, we're placing 3 identical wooden blocks in 3 liquids with different densities. The liquids are honey, water, and rubbing alcohol. Notice how the more dense the liquid is, the higher the block floats. Hence, we see the importance of the liquid's density on the buoyancy. Also, note that the higher the blocks float, the less liquid volume is being displaced. This demonstrates how the displaced volume plays a part on buoyancy as well.
So up to now, we know that buoyancy opposes gravity, buoyancy depends on the density of the fluid, and buoyancy depends on the submerged volume of the floating object. Archimedes, an ancient Greek scientist, found the following formula for buoyancy, which relates to the properties we just mentioned. Fb equals d times g times v, where Fb is the buoyancy force, d is fluid density, g is gravitational acceleration, and v is displaced volume.
Let's apply the equation to our experiment. For each fluid, if we calculate the displaced volume and multiply it by the liquid's density, we get the same value. Since the weight of each block is the same, the weight of the displaced fluid is the same in each case. This matches Archimedes' equation.
Now that we understand buoyancy, we can answer the question from the beginning of the video. A huge ship can float because it displaces a huge volume of water, whereas a rock might be light, but displaces very little. Let's use Archimedes' equation to figure out how much weight a cargo ship can carry. Our cargo ship is 250 meters long, 30 meters wide, and goes 10 meters below the water surface. Multiplying these together, we know the volume displaced by the cargo ship is 75,000 cubic meters. Multiplying by the density of water and gravitational acceleration, we get that the buoyancy force acting on the ship is 735 million newtons, or about 165 million pounds.
That means that the ship could hold 165 million pounds of weight before it sinks. That's the equivalent of 8,000 elephants, or even 170 jumbo jets.
We can also use buoyancy to explain some interesting experiments that you can try at home.
For example, one of these eggs is fresh and one was accidentally left out of the refrigerator. How can we use buoyancy to figure out which is which? Well, one floats and one sinks. What's going on?
This is a bit tricky. While eggshells look solid, they're actually porous. That means that the shell is covered in small holes. Over time, as the egg starts to rot, vapor escapes through these holes. The volume of the egg stays the same, but its mass is decreasing, so the density is also decreasing. After enough time, the egg's density becomes lower than the density of the water, and the egg begins to float.
Here's another experiment that you can try at home. What happens when you drop raisins into soda? Sometimes they're on the bottom of the glass, while other times they're at the top. What is going on?
Soda has carbon dioxide gas, which escapes as bubbles. Raisins are more dense than water and initially sink. Since raisins have wrinkled skin, the bubbles can get trapped on the surface as they try to escape. These bubbles are buoyant in water because of their low density and cause the raisins to float. After the raisins reach the surface, the bubbles pop and the raisins sink again. This process repeats and the raisins dance.
And that's buoyancy.